So that's what the intermolecular forces are. How do they affect matter? So we could not have solids or liquids without them, so that's really important. But there's some other properties, such as surface tension, viscosity, and capillary action, which are due to intermolecular forces. This is a photograph of a paperclip floating on water. What's a paperclip made out of? Probably steel. Is the density of steel greater than water or less? Greater. Steel sinks in water. Why is the paperclip floating? You see how it's distorting the surface of the water? It's almost like this was a trampoline and it's pushing down, but it's not going through. It's almost like there's a skin on top of the water. Here's a fly fishing fly. It will float on the water. You throw it out there, and it'll just sit there. You've probably seen water skater bugs, and they run around on the surface of the water. It looks kind of fun. It has to do with the surface tension. Surface tension is the tendency of a liquid to minimize its surface area. It can be measured. When they measure it, they talk about the energy required to increase the surface area by a particular amount. So water has a surface tension of 72.8 millijoules per square meter. And this is what allows things like paperclips and trout flies to float on water, even though the density says they should not. So how does this work? Well, if we look at the particles in a liquid and think about the intermolecular forces that are holding them together as a liquid. Here we have a surface molecule, and in this illustration, it is only interacting with 4 of the neighboring molecules, whereas this interior molecule is interacting with 6, right? So this surface molecule has higher potential energy because it has less interaction with its neighbors. These forces of attraction lower the potential energy. If we are to increase the surface area of this liquid, more liquid molecules are going to have to be in that less stable position of being on the surface. Does that make sense? If we're going to take this water and spread it out, we're going to have more molecules on the surface than there were before. That's not favorable energetically. This is more stable, and this surface ones are less stable. So because of this, liquids tend to minimize their surface area. What is the geometric three-dimensional shape that has the smallest surface area per unit volume? A sphere. A sphere has the smallest surface area for its volume. If you do a cube or a tetrahedron or any other shape, the surface area, the ratio of surface area to volume is going to be larger. And that's why when water falls in small drops, it forms mostly spherical drops, because that's minimizing the surface area, and that is energetically favorable. Here's a picture of a very large water droplet. This guy's on the space shuttle. And so you can make these big drops of water, and they're not going to be distorted by gravity. And they just float around, and you can look at them. Yeah, you could drink it. You just suck it in. The reason that water droplets, we think of a water droplet, I should make it blue. We think of a water droplet as being more like this, more droplet-shaped, right? Because it's distorted by gravity. When we were titrating on Tuesday, you see a drop hanging off the end of the burette, right? It's being distorted by gravity. Maybe during lab, we'll see if we can find some cool videos on YouTube. There's some really cool videos where they show things in extreme slow motion, and you can see the perfectly spherical little droplets of water flying through the air. Very, very cool. So, surface tension. Viscosity is another effect of intermolecular forces. Viscosity is resistance of a liquid to flow. If you care, it's measured with a unit called the poise, which is 1 gram per centimeter second. We find that viscosity is greater in substances that have stronger intermolecular forces. And this should make sense, okay? Okay, crazy analogy. So if you had a group of students wearing silk pajamas or a group of students wearing flannel pajamas, and they're really crowded together, and you're trying to get through them. I don't know why. Maybe there's pizza on the other side of the room and you're really hungry. And so you're trying to get through this crowd of people, and you've got silk pajamas, satin pajamas on, and you're pushing through a bunch of people in satin pajamas. Is that going to be hard? No, not too much. What if everybody's wearing flannel? It kind of sticks to itself, right? And there's resistance. It's going to take you longer to get there. So strong intermolecular forces, it takes the molecules longer to move because they're sticking to each other.
So they're all wearing flannel pajamas?
They're all wearing flannel pajamas. Well, some of them are. You know, the things like maple syrup is very viscous, right? Motor oil, it pours slowly, right? Because the molecules are wearing flannel pajamas. Or maybe polar fleece. Polar fleece could be bad too. Things like alcohol, gasoline, satin pajamas. Slippery. So viscosity is greater in substances that have stronger intermolecular forces. But this also is going to depend on molecular shape. Because we've got greater interactions if there's greater area. Here we're comparing some hydrocarbons. Pentane, hexane, heptane, octane, and nonane, all just straight chain hydrocarbons. Here's nonane, 9 carbons in a chain. You could imagine that if this one and another one lined up next to each other, they'd have a great deal of surface area, right? And so they're going to stick a lot. And we see that the viscosity is greater for that one. These can also twist around. They're kind of like cooked spaghetti, and so they can twist around and they can tangle up on each other. Whereas when you get something that's smaller, not only are the intermolecular forces of the dispersion forces going to be weaker, but there's less surface area for this one than for this one. And so we see this trend in viscosity increasing as the molar mass of these hydrocarbons increases. The place I hear about viscosity most often in real life is on the radio or on television, where they talk about viscosity breakdown in motor oil, right? The viscosity of your motor oil is important because you need it to lubricate the internal moving parts of your engine. If the viscosity breaks down, if it becomes more inviscid, more fluid, then it's not going to coat very well. It's going to tend to fall down to the bottom of the engine. It's not going to coat your engine very well, so that's bad. If your engine oil gets too viscous, like you're using a summer motor oil in the middle of the winter in Minnesota and it's really cold, what happens to the viscosity of maple syrup if you put it in the refrigerator? Does it get thicker or thinner? It gets much thicker, doesn't it? And honey is viscous as well. At colder temperatures, the strength of the intermolecular forces is even greater and it flows less well. So if you've got your engine oil that maybe it has a lot of gunk in it, or maybe it's just too cold for it and it gets really thick, then your engine can't move very well either, and that's going to be a problem. So it depends on temperature. Viscosity does. At high temperatures, there's more thermal energy, which can partially overcome those intermolecular forces, and the molecules can flow a little more freely. You take that maple syrup and you heat it up in the microwave, and it becomes more watery, more runny, right? Same thing with honey. What they've done in modern motor oils is really, really cool. They have some polymers that they put in them, and at low temperatures, the polymers coil up. If the polymer coils, what does that do to its surface area? If it goes from a long, straight thing to a curled up thing, it decreases the surface area of that molecule. If there's less surface area for it to interact with other molecules, the strength of the intermolecular forces will go down. So at cold temperatures, because the polymer curls up into a ball, the effective temperature on viscosity is minimized. At higher temperatures, they unwind and the viscosity increases. And so it moderates the changes in viscosity. So cool, chemistry making better motor oil. No? Whatever. Capillary action. Capillary action is the ability of a liquid to flow against gravity up a narrow tube. So here's a picture, 3 different tubes in a liquid, and we see that water has risen up this tube a fair amount and up this tube only a little bit. Why does it do that? Would it do this in a large diameter tube? No. We know from our experience with drinking straws, right, that water doesn't just come up the tube. It doesn't. But in a very small tube, a capillary tube, where the diameter is very small, it does. And the distance that it rises is going to depend on the forces. There's 2 forces at work here. There's cohesive forces and adhesive forces. The cohesive forces are attraction between the molecules. So the strength of the intermolecular forces of the molecules with the other molecules of that liquid substance. Adhesive is the attraction between the liquid and the surface of the tube. So here you have a molecule, and if it's very attracted to the adhesive, if the adhesive force is great, it's very attracted to the wall of the glass, it's going to pull up some of its friends below it. And so the stronger the adhesive force, the higher the liquid will rise. The diameter of the tube is also going to matter because these molecules along the edge here, because there's more space in the middle, they're having to pull up more other molecules than the ones in these narrow tubes. Also related to capillary action, well, here's mercury, the video. This is water in a test tube, and this has this familiar meniscus, right? It almost looks like there's a contact lens sitting on top. And the water goes up at the sides, and we've all seen this as we've made measurements in burettes and volumetric flasks and all kinds of things. It goes up because of those adhesive forces. The adhesive forces are greater than the cohesive forces. If we look at mercury, Mercury's meniscus goes the other way. It's concave. It bumps up in the middle. It has cohesive forces that are greater than adhesive forces, and so it would rather stick to itself than to the glass. You can also see differences like this if you're not using glass. You can get water to have a concave meniscus also if you use certain kinds of plastic that the water is not attracted to. And then it's kind of like trying to stay away from it. Here it's like trying to climb the walls, and the mercury is like, yeah, get me away from the glass.